Hello, I'm FJezequel, and I'm happy today to present our work on a fast computation approach for trustworthy results of floating point computations. This work has been carried out with my colleagues, Steph Graya and Roman Yakimchuk, from Sorbonne University in France, and also with Daishi Mukunoki and Toshiyuki Imamura from Riken in Japan. So, as you know, the power of current computers tend to increase, and accelerators such as GPUs, TPUs, FPGAs contribute to this power. So that enables us to solve more and more complex problems. But a high number of floating point operations are performed, and each of them can lead to a rounding error. So there's a need for numerical validation, but the drawback is that existing numerical validation methods are costful. You have their execution time overhead, and there's also a development cost which is induced by the application of these methods to high performance codes. So our question today is, can we address this cost problem and still get trustworthy results? And the answer is yes, when the input data is affected by rounding or measurement errors, which is a common situation. So first I will present approaches for estimating rounding errors, and in particular, discrete stochastic arithmetic and the CATNA library that implements it. Then I will show the error induced by perturbed data. I will present our approach, which consists in combining DSA and standard floating point arithmetic. I will present numerical experiments that cover two aspects, the accuracy and the performance. And then I will discuss the advantages and the disadvantages of our approach. So rounding errors can be analyzed using a probabilistic approach. With such an approach, operations are performed several times with random perturbations. And so from the different results obtained, the accuracy can be estimated. One advantage is that the user code is directly analyzed. There's no need for specific numerical algorithms to solve the user problem. I give here a list of tools that implement such an approach. I tried to give the year of the first version of each one. These tools differ by several aspects, such as the number of executions, the way perturbations are carried out, their ability to detect numerical instabilities. One of these probabilistic methods is discrete stochastic arithmetic. So with DSA, each arithmetic operation is performed 3 times with a random rounding mode. So we don't get one result R, but 3 results, where each one is rounded up or down with the same probability. And the number of correct digits in the results is estimated using students' test with the confidence level 95%. One advantage of this approach is that operations are executed in a synchronous way. So that means one arithmetic operation is executed 3 times, and then the next arithmetic operation is executed. So numerical instabilities can be detected. For instance, if you have a test with 2 operands, and the difference between these operands is numerical noise, you will be informed. Another advantage is that with such an approach, you are able to optimize stopping criteria. With an iterative process, you can stop when the difference between 2 successive iterates is numerical noise. And this approach is implemented in the Cadna library that can be used to control accuracy in programs that use double, single, or half precision variables. And it can be used also in programs that use arbitrary precision to solve unstable problems. So the Cadna library allows us to estimate rounding error propagation in scientific codes written in C, C++, or Fortran. Cadna enables one to estimate the number of correct digits in any result and also to detect numerical instabilities, which are usually due to numerical noise. Cadna actually provides new numerical types, which are called the stochastic types, and they consist of 3 floating point variables and 1 integer to store the accuracy. And all operators, all mathematical functions are redefined for these types. So Cadna actually requires only a few modifications in user programs. And of course, Cadna has a cost. The cost in memory is 4, and the cost in execution time is about 10. But of course, it depends on the instability detection level. It depends on the fact that the initial code may be very well optimized for classic floating point arithmetic. So now I would like to show you an example with and without Cadna. We want to compute this expression for 2 different couples, x and y. And first we run the code without Cadna, and we get this result. P1 is 2 with plenty of zeros, and P2 has a different value. But we have no information on the accuracy of these results. So we decide to use this code with Cadna. So to do it, we have to include the Cadna library. We have to call an initialization function. -1 here means that we'll detect all kinds of numerical instabilities. With this termination function, we get the instability report. We have to change the types from classic floating point variables to stochastic variables. And here we have a format, an output format, and we have to change it because we use Cadna specific function that will print out the results only with their correct digits. And so we print a string here. That's why we have to change the format. And here you have the output. So you see that we detect all kinds of instabilities. For P1, we get a result which is numerical noise, which has no correct digits. And for P2, we get 15 correct digits. And you can have a closer look at the floating point values in P1 and P2. And you can see that in P1, we get actually 3 floating point values which have no correct digit. And in P2, you have 3 floating point values which have 15 correct digits in common. Okay, and you also have 2 numerical instabilities which are detected. So 2 catastrophic cancellations. So that means that we have subtracted 2 close values affected by rounding errors. So now I'm going to show you the error induced by perturbed data. Here we denote by y, which is f of x, an exact result, and y hat, f hat of x, is the computed result. So they are different because of the finite precision of the computer. And the forward error is the difference between the exact and the computed result. And the backward analysis tries to seek for delta x such that y hat is f of x plus delta x. Delta x is the backward error associated with y hat. It measures the distance between the problems that is actually solved and the initial one. Here you also have the definition for the condition number C of the problem. It measures the effect on the result of data perturbation, delta X. Here we use a classic notation U to represent the relative rounding error. So you have the value of U in double precision and in single precision. And if the algorithm is backward stable, so that means the backward error is of the order of U, the relative error on f hat of X is about CU. And if the input data are perturbed, so that means the input data are not X, but X hat with a relative error delta, then one computes f hat of X hat with a relative error, which is C multiplied by U plus absolute value of delta. And if the order of magnitude is delta is greater than U, the rounding error generated by f hat, which is CU, is negligible with respect to C delta. And so estimating this rounding error CU may be avoided. So now I will present our approach, which consists in combining DSA and standard floating point arithmetic. So here, computation routines are executed in a code that is controlled using DSA, for instance, with Cadna. Their input data are affected by errors. That can be rounding errors, measurement errors. And we want to compare two kinds of computation with a call to Cadna routines and with three calls to classic floating point routines. So first with Cadna routines, we have stochastic data, D. We use the routine and we get a stochastic result, R. D and R consist in stochastic arrays. Each element in D and R is a triplet. And of course, because we use Cadna, every arithmetic operation is performed 3 times with the random rounding mode. So now we want to perform the computation with 3 calls to classic floating point routines. So we have the stochastic data D, and from D, we will create 3 classic floating point arrays, D1, D2, D3. These 3 arrays are created from the triplets of D. We perform the computation and then we get 3 classic floating point arrays, and a stochastic array R prime will be created from these 3 classic arrays. And the stochastic result R prime can be used in the next parts of the code that will use Cadna. And so we want to compare the number of correct digits, which is estimated by Cadna, in the stochastic result R and the stochastic result R prime. So now I'm going to show you our numerical experiments. First, the experiments, we will cover the accuracy aspect. So we initialize the stochastic values. Each stochastic values is initialized as alpha 10 to e, where alpha is a random variable uniformly distributed in -1, 1, and e is an integer randomly generated in 0e. In double precision, we have chosen to set e to 20, and in single precision, e is set to 3. So we generate random data with different orders of magnitude, and then each input value is perturbed with a relative error delta. We use a Cadna function for that. Then we will analyze the accuracy. So for each element in R and R prime, we will get its accuracy, and we will compute the difference between the two accuracy. So first, we want to multiply square random matrices of size 500 in double and in single precision. In this table, we report the perturbation delta, the accuracy of R, so the mean value, the minimum, and the maximum value of the accuracy of all the elements in R. And we also have the accuracy difference between R and R prime. So the mean value of the differences and the maximum value of the differences. Okay, so you can see that as the order of magnitude of delta increases, the mean accuracy decreases by 1 digit. And as expected, with a high perturbation in single precision, you get a low accuracy on the results. And we can see that there's a low difference between the accuracy of R and R prime. You also have the results obtained for the multiplication of a square random matrix of size 1000 with a vector. So again, in single and then in double and then in single precision. And again, as the order of magnitude of delta increases, the mean accuracy decreases by 1 digit. And again, as expected, a high perturbation in single precision results in a low accuracy on the computed results. And you can see that the accuracy difference between R and R prime remains low. And in particular, in double precision, all the results have the same accuracy if delta is greater than 10 to minus 12. So now the performance comparison. So we'll run codes for matrix multiplication and codes for matrix vector multiplication. We analyze the performance of various double precision codes. So first, CADNA, that performs naive sequential multiplication with CADNA. So here, naive means that it's a multiplication, classic, non-optimized multiplication with nested loops. We have the naive sequential codes. So they implement our approach using a sequential naive multiplication. You have what is called naive OpenMP that implements our approach using a naive parallel multiplication that relies on OpenMP. Here we use 4 cores. We have MKL sequential that implements our approach using a sequential BLAS routine from the Intel MKL library. And then we have the MKL OpenMP that implements our approach using a parallel MKL BLAS routine. And as a remark, array copies are performed, of course, except with the CADNA version. So why these array copies? So you have stochastic data, you perform 3 times the computation with classic BLAS routines, and then we get a stochastic result. So you see that there are conversions between array of structures and structure of arrays. Before the BLAS routine, you have from a stochastic array to obtain 3 classic arrays. And after the BLAS routine, from 3 classic floating point arrays, you will create a stochastic array. And this situation is the worst case because the array copy cost in the total execution time is maximum here because we use only 1 BLAS routine. when BLAS routines are continuously used, the array copies are performed only before and after them. As a remark here, both computation and array copies are parallelized in the OpenMP codes. So you have here the performance for matrix multiplication. So for different matrix sizes, we have the execution time of all the codes. And we see that despite memory copies, the codes using 3 classic matrix multiplications perform better than the CATNA routine. And in particular, for matrices of size 2000, you can see that the MKL OpenMP implementation outperforms the CATNA routine by a factor which is nearly 300. Here you have the execution time for matrices of size 2000. In blue, you have the computation time due to the multiplications, and in red, the time due to the array copies. And you can see that most of the execution time is spent in matrix multiplication. So here you have 2 tables, still for matrix multiplication. The first one has been obtained with matrices of size 2000 using 4 cores. And the second table has been obtained for matrices of size 5000 with 24 cores. And so you can see here that on large scale, the performance gain increases. In the second table, you can see a speed up of about 3,800. And you can see also that the array copy cost becomes visible here because on many cores, the computation is efficiently performed. Okay, so you have here the performance obtained for matrix vector multiplication. And so you can see that the CADNA routine in blue performs better than the other sequential codes. But from a certain matrix size, the OpenMP codes that use classic floating point arithmetic perform better than the CADNA code. So again, we want to see the time spent here for matrices of size 10,000, the time spent in computation and the time spent in array copies. And you can see that in the sequential codes that use classic floating point arithmetic, the main part of the execution time is spent in array copies. And as a recall, in the OpenMP versions, the array copies are parallelized. Okay, so now I'm going to discuss the advantages and disadvantages of our approach. So one advantage, of course, is performance gain, because DSA operations are avoided. In particular, we don't use a random rounding mode. We don't detect instabilities. And another advantage is that we can use vendor very optimized libraries. The other advantage is the applicability. You don't need to translate your code into a CADNA version. But of course, there are disadvantages. We lose the CADNA features, for instance, the instability detection, and you cannot approve the accuracy, which is possible sometimes in CADNA codes. So without CADNA, with our approach, numerical instabilities cannot be detected, of course, but you can get results with no correct digits that will appear as numerical noise. Here, for example, we multiply matrices that will generate catastrophic cancellations. So we have very small matrices, square matrices A and B of size 10 in double precision. And the first line of A contains 5 times 1 and 5 times -1. Each element in the matrix B is set to 1, and A and B are perturbed with a relative error delta, which is 10 to -12. So we compute C equals A times B with cadenas, and C prime, which is also A times B without cadenas, with our approach. And you can see that the first line of C and C prime, which should be 0, contains numerical noise. So each value is a triplet with no common digits. And with cadenas, you have an additional information. You know that 10 catastrophic cancellations are detected. Okay, so the other advantage of cadenas is the accuracy improvement. Here we have, as an example, the application of Gauss algorithm with pivoting. So we want to solve this linear system in single precision, and A and B are perturbed with a relative error 10 to -6. And we get X with cadenas, X prime without cadenas. And so you can see that without cadenas, in X prime, you get numerical noise. And with cadenas, the accuracy is much more satisfactory. And what happens here? There's a test for pivoting. And with cadenas, when you get a value A of ij, which is numerical noise, which is non-significant, then the answer of the test is false. So with cadenas, a non-significant element is not chosen as a pivot. And without cadenas, this non-significant element is chosen as a pivot. So with cadenas, you also have the instability report. So you are informed that there's an unstable branching. You also have an instability which is due to the absolute value, and you also perform here one catastrophic cancellation. So as a conclusion, in a code controlled using cadenas, if computation-intensive routines are run with perturbed data, classic blast routines can be executed 3 times instead of the cadenas routines, and as you have seen, with almost no accuracy difference on the results. The performance gain can be high with blast routines from an optimized library, especially on a many-core architecture, but we lose the instability detection, which is a nice feature of cadenas. The same conclusions would be valid with an HPC code using an MPI, the MPI standard for communication, in the same conditions. So computation-intensive routines and perturbed data. The cadenas MPI routines could be replaced by optimized floating point MPI routines. And another perspective, because our experiments use synthetic input data, we plan to apply our approach to real-life examples with realistic data sets. So I would like to thank you for your attention. And if you have questions, I will be very happy to answer them during the conference.